Hello everyone, welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have these lecture slides, you may refer to my GitHub page at this given link. So today lecture, we are going to discuss the Bayesian decision theory. In the Bayesian decision theory, we would be discussing the Bayesian decision classifier, which is a nonlinear classifier. Means it can classify the nonlinearly separable data samples. It is based on the fundamental statistical approach that quantifies the trade-off between various decisions and cost that accompany such decisions. And also it is based on Bayes theorem. To understand the Bayes theorem, let us consider a fish sorting example where we consider that there are two types of fish. One fish is sea bass and the another fish is salmon. So if we define type of fish as random variable, then we can define our state of nature or class as a random variable in case of a sorting problem. Then here our state of nature or class label will be, so suppose omega is a random variable which define the class label, then it will be omega 1 for sea bass and omega is omega 2 for salmon. Okay, then we can define the prior probability for the individual class as p of omega 1, which is the prior probability that the next fish is a sea bass. Okay, and the prior probability for class 2 is the prior probability that the next fish is a salmon. Okay, so this is the prior probability that that is known to us. So basically the prior probabilities reflect our knowledge of how likely each type of fish will appear before we actually see it, because it is the classification problem for fish sorting. But how we can choose these prior probabilities? In this case, we set P1 equal to P2. That means the prior probability of class omega 1 is equal to the prior probability of class omega 2 if the finding phases are equiprobable. Okay, that means for the phase classification problem, if the finding of phases are equally probable, then the finding the phase or finding the sea bass or finding the salmon is equal. Or we may choose or we may use different values depending on the fishing area or time of year, etc. That means the prior probability we can decide based on the fishing area or the time of year in which time span we are collecting the fish. And if we have no other type of fish, then we can say that the prior probability of class 1 plus the prior probability of class 2 is equal to 1. So this case is called the exclusively and exhaustively, because we don't have the other fish, the only two fish is there. That is why it is exhaustivity, and it is exclusively because the summation of the probability of these two fish is equal to 1. So we can say that it is exclusively and exhaustively. So based on this prior information, we can make the decision. And how we can make the decision? That we have to decide class omega 1 if the prior probability of omega 1 is greater than prior probability of omega 2. That means we will find that the fish is sea bass if the prior probability of sea bass is greater than the prior probability of salmon, and we will consider it as omega 2 otherwise. So this is the decision rule based on the prior information. And how much error it will occur if we will make this decision. So the probability of error for this decision is minimum of the prior probability of P omega 1 and P of omega 2. So here the probability of error will be the minimum of these two prior probability. So don't you feel that there is some problem in making a decision? Because if we have some information, and that is the prior information, which is the prior probability, that if the prior probability of C bus is 0.8, then we will have the prior probability of C bus as 0.2. So in this case, we will always make the decision in favor of C bus. Okay. So in this decision rule, there is some problem. So let us generalize this decision rule by adding some more information to this decision rule. So we can improve the decision using some lightness feature of the fish. So suppose we consider the lightness of these two different fish, then we can improve the decision. So if we consider lightness feature, which is a random variable here, then decision can be improved. So note down here that we are considering only one feature, that is the lightness, and which is a continuous random variable. Then if x is our random variable, which is continuous random variable, then we can define the probability density function px which defines as the frequency of measuring a pattern of fish with feature vector x, and this is called evidence. So here we are considering the lightness feature of all the fish, whether it is salmon or sea bass, and it is denoted by small p of x. We can also define the class conditional probability, which is denoted as small p of x given omega j. This is called class conditional probability, or likelihood. So this is defined as how frequently we will measure a pattern with feature value x, given that pattern belong to class omega j. So here the class conditional probability of class 1 and class conditional probability of class 2 describe the difference in lightness between population of sea bass and salmon. So here basically the class conditional probability of class 1 is the distribution or population of sea bass, and the class conditional probability of class omega 2 is the distribution of the population of salmon fish. So in this figure you can find that this is a hypothetical class conditional probability density function of salmon and class conditional probability density function of sea bass. So if we know the prior probability of jth class and their class conditional probability for j equal to 1 and 2, because we have the two class that we have considered, that is for 1 for first j equal to 1 is for salmon and j equal to 2 for sea bass. So if we know the prior probability and likelihood, then using Bayes formula or Bayes rule, we can define the posterior probability in terms of prior probability and likelihood. So how we can define the posterior probability P of omega j given x equal to the likelihood into the prior probability divided by the evidence. So we can write likelihood into prior divided by evidence, where P of omega j given x is the posterior probability and the evidence is defined as using this expression. Okay, so limit is from j equal to 1 to 2 because we have considered the two class problem. So if we compute the posterior probability of the hypothetical class conditional probability density function that I have shown to you, so this is the class conditional probability, we can compute the posterior probability. So if we will compute the posterior probability by considering the prior probability as p omega 1 equal to 2 by 3 and p of omega 2 as 1 by 3, then we will obtain the posterior probability as using this plot, where this black line shows the C bars, the posterior probability for C bars, and red line shows the posterior probability for Salmon. So if you will consider one example, that in this plot, if we observe that a pattern is measured to have feature value x equal to 14. So suppose we have lightness feature value is 14, then we can compute the posterior value at this feature value. Then the posterior probability will be p omega 1 given x equal to 0.0 2 and p of omega 1 given x equal to 0.92. So here, if any fish comes and its lightness value is 14, then we can say that that fish belongs to the class omega 1. That means the probability of occurrence of this fish as C bars is maximum. So we will decide that if any fish having the lightness as 14, then the fish will be the C bars. And also we can note down that the probability of omega 1 given x and probability of omega 2 given x equal to 0.92 plus 0.08 equal to 1. So for every value of x, the posterior sum will be equal to 1. Now our decision rule, it will be decide omega 1 if the posterior probability of class 1 is greater than posterior probability of class 2. Otherwise, we will decide omega 2. Okay. The same decision rule can be written as also decide class omega 1 if p of x given omega 1, that is the class conditional probability of class 1 into prior probability of class 1 is greater than class conditional probability of class 2 into prior probability of class 2. Otherwise, we will decide omega 2. So because Px is common for both the classes, so it is not contribute to make any decision. That's why the evidence term is omitted in this decision rule. So if we will make this decision, then what will be our probability of error? probability of error given the feature x equal to, so the probability of error will be the p of omega 1 given x if we decide omega 2. Okay, so if we decide class 2, then the probability of error will be the prior probability of class 1, sorry, posterior probability of class 1, and the probability of error will be the posterior probability of class 2 if we decide omega 1. Okay, so the Bayes decision rule minimizes this error, so we can write p of error given x equal to minimum of these two posterior probability. So in this case, we have considered only one dimensional feature, that is x, and only two class we have considered. So now we can generalize this Bayes decision rule by considering the different cases. So how we can generalize the Bayes decision rule? So to generalize the Bayes decision rule, we need to use more than one feature. So x1, x2, xd, like lightness, width of fish, number of fins of fish. So these features can be included to generalize the Bayes decision rule. Here we can use more than two class. So omega 1, omega 2 and omega c. That means we can have the c number of class. We can take some action not only decide the class. So we can make the action alpha 1, alpha 2 and alpha a. And also we will not only compute or consider probability of error, here we can introduce a loss function, and suppose lambda alpha I omega given omega j is our loss function, which is loss incurred for taking action alpha I while the true state of nature is omega j. So here lambda I given omega j is loss incurred for taking action alpha I while the true state of nature is omega j. So we will consider one by one to generalize our Bayes decision rule. So suppose first we consider C class problem. So we have C number of classes and we have d-dimensional feature vector. So if we consider the d-dimensional feature vector, then we have to consider the random variable x as upright alphabet, and if it will be a single feature component, then it will be the small or italic alphabet. So here x is d-dimensional feature vector. So then our Bayes decision rule will change according to this consideration. So before that, we can define our Bayes rule. We can define our Bayes theorem as P of omega j. So here we are using omega j instead of omega 1 and omega 2 because we have C number of classes given x. So x is now upright letter, and then likelihood into prior probability divided by evidence. Okay, so here P of x is evidence, and it can be calculated as the likelihood into the prior probability of jth class. So we will take the summation over all the classes. Okay, then our decision rule will be decide omega I if posterior probability of class omega I is greater than posterior probability of class J, where all J is not equal to I. So this condition is for all J but not equal to J equal to I. Now suppose we observe a feature vector x and alpha I action is taken. So now we are introducing the action. Suppose we observe x and alpha I action is taken. Okay, then in this case the loss incurred is defined as lambda alpha I given omega j, which is the loss incurred for taking action alpha I while the true state of nature is omega j. Okay, then we will incur some loss. That means we will expect some loss. So expected loss can be given in terms of the risk, which is defined as r alpha I given x. That means this is the risk to take the action alpha I, while our observation is feature vector x. Then we will compute the risk for all the individual classes, which is lambda alpha I given omega j into the posterior probability of class omega j, and we will take the sum for all the classes. Okay, so this is called conditional risk for taking action alpha I. Okay, now we want to find a decision rule that minimize the overall risk, because our objective is to minimize the risk. Whatever the loss we have incurred, based on that we want to minimize the risk. So in that case, the Bayes decision rule minimize the overall risk by selecting the action alpha I from set of actions for which r omega I given x is minimum. Then the resulting minimum overall risk is called the Bayes risk. So this is called so if we make a decision, that means if a Bayes decision rule, a Bayes decision rule that minimizes the overall risk by taking action alpha I from set of action for which risk is minimum. Okay, and this risk is called the Bayes risk. Okay, now let us consider the two category classification problem to minimize the risk. So suppose we have two category classification problem. And here alpha 1 is deciding when true state of nature or the true class is omega 1, and take the action alpha 2 deciding when true state of nature omega 2. So here we can write lambda alpha I omega j, and which is the loss incurred for deciding alpha I action when the true state of nature is omega j. So we can write this one as lambda ij for the notational convenience. So we can define the risk for these two class as r alpha 1 given x equal to lambda 1 1 and posterior probability of class 1 plus lambda 1 2 into posterior probability of class 2. Similarly, we can compute the risk for class 2, which is lambda 2 1 into posterior probability of class 1 plus lambda 2 2 into posterior probability of class 2. Okay, so the fundamental decision rule we can define. So our decision rule will be decide omega 1. Here we have to minimize the risk. That means we have to consider omega 1 if the risk of class 1 is less than risk of taking action alpha 2, where either. So here we will take the decision in favor of omega 1 if the risk of class 1 is less than risk of class 2, otherwise omega 2. Okay, and this is called the minimum risk classifier. This decision rule is for the minimum risk classifier. Okay, now let us analyze this expression, which is the condition to decide the class omega 1. So here R alpha 1 given x is less than R alpha 2 given x, then we can put the value from the previous expression. We can put these equations. Then just simplify by taking the common the posterior probabilities. So we will have lambda 1 2 lambda 2 2 into p of omega 2 given x is less than lambda 2 1 minus lambda 1 1 into p of omega 1 given x. Then we can write just reverse right hand side and left hand side. Just we are swapping it so that our inequality will change. P omega 1 given x greater than lambda 1 2 minus lambda 2 2 into p of omega 2 given x. Then we can write lambda 2 1 minus lambda 1 1. So instead of posterior probability, we can write the likelihood into the prior probability of class 1. Similarly, on the right hand side, we can write p of x omega 2 into p of omega 2. Now take the ratio of likelihood and we will obtain lambda 1 2 minus lambda 2 2 divided by lambda 2 1 minus lambda 1 1, okay, into p of omega 2 divided by p of omega 1. So this is called the likelihood ratio. Okay, so if the likelihood ratio exceeds this threshold, then if the likelihood ratio exceeds this threshold value independent of the input pattern x. So if you can notice here that this threshold value is independent of x, then we can make the optimal decision. Okay, so just see, if we have the likelihood ratio is something like this, and then just put a threshold theta, this is p of x omega 1 divided by p of x omega 2 likelihood ratio, and if it exceeds some threshold, then it will be class 1. So this will be for region 1 and this will be region 2, because this is less than the threshold value. Okay, so this likelihood ratio helps us to make the decision. Now let us discuss the minimum error rate classification. That means how the minimum risk classifier is converted to minimum error rate classification problem. So here we are seeking a decision rule in case of minimum error rate classification problem such that it minimizes the probability of error, which is the error rate. So in this case, if we define our loss function as 0, 1 loss function, then our minimum risk classifier will convert to the minimum error rate classifier. So what is the 0, 1 loss function? How we can define it? So just define 0, 1 loss function as lambda alpha I omega j equal to 0, 1 if I equal to j and if I not equal to j. For I, j is the class level. Okay, then we can compute the conditional risk. Conditional risk becomes lambda ri given x equal to, we know the expression as lambda alpha I given omega j into the posterior probability for all the classes, summation over all the classes. So if we put this value from this 0, 1 loss function, then we will obtain that it is 1 only when I is not equal to j. So we can write p of omega j given x when I not equal to j. Okay, or we can write j not equal to I. Okay, and we know that the summation of all the posterior probability is 1, so we can write that 1 minus and the posterior probability of class I. Okay, this is the same thing. Okay, so minimizing the risk means we need to maximize the posterior probability, because we want to minimize the risk, so definitely we have to maximize the posterior probability. So our minimum error decision rule is decide omega I if p of omega I given x is greater than p of omega j given x for all j not equal to I. So already we have seen this expression. That means the Bayes decision rule is also, it gives the minimum error rate when we make the decision using this decision rule. Okay, So this much for this lecture. Thank you.